All right. Oh,
Bailey.
and this is actually 10-3. I'm really didn't do a very good job last year of changing that. All right. So, parametric calculus. The derivative dy dx of a parametric function is dy dt over dx dt. Because the dt's cancel and we're left with dy dx. You can see why it's a problem if both dy dt and dx dt are simultaneously 0. If we have 0 over 0, all right? Remember that is when...
What when just dx equals 0?
If just dx dt equals 0, then we would probably have a vertical tangent. If dy dt equals 0, we have a horizontal. We have not smooth when they're both 0. Okay? Are you ready? You actually have to, excuse me, you have what you need.
Got it.
Okay, so let's go ahead and find the derivative, well, find the equation of the tangent line to this equation at t equals 2. So go ahead and write down the parametric equations. So dy dx is dy dt over dx dt. Okay? So dy dt would be what? dy dt, what's the derivative of what?
6t squared.
Over derivative of x. Okay? If I ask for just the derivative, you would be done. Okay? But I did not ask for just the derivative. I want the derivative, first of all, evaluated when t equals 2. Okay? So if t equals 2, what's our derivative?
Did you drop a square note?
It's a little delayed.
19/4.
19/4. Okay. As we recall from calculus 1, 19/4 is our slope. Okay. Now, when we write a tangent line equation for a parametric curve, we are going to write it as a rectangular equation in terms of y and x. So at t equals 2, what's our coordinate? We plug 2 in for the x, what do we get?
You get 5 for the x.
Aaron, just put yourself on the couch back there.
Oh,
5 and what?
6.
Okay, so our tangent line equation is, do you have a castigate to your second arm?
Yeah.
Okay. Y minus 6 equals 19/4 times x minus. Does it really seem like a curveball?
Not yet. No, but Josh just won the club. That's saying it doesn't seem so bad.
You jinxed it.
Find the points where the tangent line to this curve is horizontal. Ricky, you'll be close enough. Okay.
Thank you.
Okay, so our derivative has to do with our tangent lines and their slope. So let's find dy dx. dy dt would be 6t squared minus 24 over the xct would be 2t plus 6. Okay, now if we're looking for points of horizontal tangency, then we care about what? The numerator and where it equals 0. So we want 6t squared minus 24 to equal 0. What? T equals plus or minus 2? Okay. So, since we do want the points of horizontal tangency, what do we need to do with 2 and negative 2? Okay, so we need to come back to here. So, when t is 2, we have the coordinate, let's see, 4 plus 24, right? 28, so 16 minus 48. Are you good with those calculations?
This is for positive?
Yeah. You'd have 4 plus 24, right?
It'd be 4 plus 12.
Yeah.
Yeah,
16.
12.
Oh, I was multiplying. Yeah.
So would it be like 16?
Yeah. 4 was stuck in my head. Okay, so when t is negative 2, thanks for catching that. Try to pay attention. We have 4 minus 12, right?
30.
And we would have negative,
We have a positive 30.
we have negative 16 plus 30.
48.
There we go. We got there. Those are our 2 points of horizontal tangency. You want to see what this looks like in a calculator?
Sure.
Okay, so I'm going to have to change my mode to parametric. All right, what were our 2 equations? T squared plus 6t? And 2t cubed minus 24t. Okay, now my t is set up so that t starts at 0. So if we say like negative 6 to 6 for t, and we'll see all of it. So there are 2 places of horizontal tangency. T is -2, T is +2. Cool. What do you think my next example is going to be?
Trick.
Curveball rule.
Vertical tangency. Same equation though, right? Okay, so same equation. Now we're going to do vertical tangency. So from the last slide, we have dy dx was 6t minus 6t squared minus 24 over 2t plus 6. So now for vertical tangency, we want the denominator to be 0, which means t is what?
-3.
T is -3. Okay, and since we're asked for the points of vertical tangency, we need to plug t is -3 into our parametric equation to get okay.
Yeah.
Now, luckily, these did not overlap. But what you will need to make sure is that if you find a point of horizontal tangency, you want to make sure that that does not also make the other derivative 0. So we found here where dy dt equals 0. If 2 made dx dt 0, it would not be a point of horizontal tangency because our curve would not be smooth. Okay? Because if both of them are 0, we're not smooth. So here it was okay because we found both, and so then we could compare at the end, right? But if I only ask you for horizontal tangency, you will want to make sure that that t value also does not make your denominator 0. Does that make sense? Okay, so you'll have to check that. All right. Now, here's maybe where your curveball comes in. Here is how you find the second derivative. Go ahead and write it down and I'll explain what it means. Terrifying.
It looks pretty scary.
Can we use this for? Wait, you want to just take the derivative? Okay. Okay, she said.
Just write it down so that you have the notation in front of you. Yeah, quotient rule will come in. Okay, so what does all of these letters mean? Okay, this right here, d dt of dy dx, that means take the derivative of dy dx with respect to t. Okay, when we take our derivative, right, it's going to be in terms of t. So you're going to take your first derivative and take the derivative with respect to t, but then you have to divide it by dx dt. So we have to keep in mind that it's a parametric equation. So just like to find dy dx, we take dy dt over dx dt. For our second derivative, we take the derivative of y over dx dt.
And only dx dt cannot equal 0?
Correct. Okay. The same could be said about the third derivative. If we wanted to find the third derivative, which we won't, parametrically, we could take the derivative of the second derivative and divide it by dx dt. Okay, won't make you do that, but that's how we do it. Okay. So, here we go. Is this function concave up or concave down? Go ahead and write it down. Okay, so if we're talking about concavity, we need the second derivative. Let's first find dy dx. dy dx is dy dt over dx dt. So dy dt is 3t squared minus 2t. dx dt is 2t minus 2. Can this be reduced at all?
But I don't think it helps.
No. Okay.
Like if you take out the 2's and you could take out the t's from the numerator, 2 from the
Right, we could try, but nothing's going to cancel. Okay? So, that's all right. On to the second derivative. The second derivative means we are taking the derivative of our first derivative with respect to t and dividing it by dx dt. Okay, well, we have a fraction, which means we get to use the quotient rule, right? So derivative of our numerator is 6t minus 2 times our denominator minus our numerator times the derivative of our denominator all over our denominator squared. Okay. Now what's nice about this is if you do have to use your quotient rule, then you have something similar in the denominator of your second derivative, right? This is dx dt squared if we do the quotient rule, and here we have dx dt. So we can squish these together for 2t minus 2 cubed. Okay, and then we have that numerator to simplify. So we can multiply everything out and then combine like terms. So I have 18 squared minus 6t minus 4t plus 4 minus the quantity 6t squared minus 4t.
Wait, 18t squared.
Is 12. My calculator up here is not working very well today. Okay. When we combine like terms, what are we left with? How many t squareds?
This one.
6. Yep.
Isn't negative, or 6t times negative 2, negative 12t, not negative 6t?
This right here?
Yeah, I think so.
I was seeing a t, another 2t. That's fun. So we have 6t squared minus 12t plus 1. Okay. And we can factor out a 2 in the numerator, but it's not going to help us simplify it, so I would just leave it like that. Okay? So if I ask simply for the second derivative, that would be it. Okay? But of course, I'm going to ask you to do something with it for this example, because why not? We want to know if we are concave up or concave down at the point 0,4. Well, my second derivative is in terms of t. How do I figure out our concavity at 0,4?
Solve for 0, 4.
Okay, this means that 0 equals t squared minus 2t, and 4 equals t cubed minus t squared. So that means t is 2. Come back up to here. This is t times t minus 2. Obviously, t can't be 0, otherwise y would also be 0. So t has to be 2. So we can come down here now and evaluate this at t equals 2. We have 24 minus 24 plus 4 over 4 minus 2 cubed. What kind of number is that?
Positive 1.
Are we concave down?
No.
No, we're concave up because our second derivative is positive.
So is there ever going to be a time where we have to apply those rules for parametrics?